Welcome back to Science Aura. I'm Dr. Sachi Vale. Today we dissect the ultimate high-stakes chess game played in the silent skies above our world. For decades, the United States has maintained absolute aerial dominance through the magic of stealth technology. Aircraft like the F-35 Lightning II are engineered to be virtually invisible to radar, slipping through defensive nets like ghosts. But a fundamental law of the universe is about to shatter this illusion of complete invisibility. To understand how this illusion is broken, we must first look at how stealth works. Traditional radar relies on sending out radio waves and measuring how they bounce back off an object. If an aircraft has flat, angled surfaces and is coated with radar-absorbent materials, these waves are scattered away from the source or absorbed entirely. To a ground radar station, a massive multi-million-dollar fighter jet appears no larger than a tiny sparrow. This technological marvel did not come cheap. Billions of dollars and decades of intensive research have been poured into perfecting these stealth shapes. The United States and its allies built their entire modern military strategy around the assumption that their jets could operate with complete impunity in contested airspace. But this massive engineering achievement has a glaring, unavoidable Achilles heel that radar cannot protect against. That Achilles heel is heat. No matter how advanced an aircraft's radar-absorbent coating is, it cannot escape the unyielding laws of thermodynamics. To fly at supersonic speeds, to carry heavy payloads, and to power complex avionics, a jet engine must burn fuel. This combustion process generates an immense amount of thermal energy, creating a massive temperature differential between the aircraft and the freezing cold sky surrounding it. According to the second law of thermodynamics, heat naturally flows from hotter regions to colder ones. A jet engine cannot operate in a closed loop. It must continuously expel its superheated exhaust gases into the atmosphere. This means that even if an F-35 is completely invisible to electromagnetic radar waves, it is simultaneously acting as a screaming beacon of thermal energy, radiating heat into the cold upper atmosphere. This phenomenon is governed by Planck's law of blackbody radiation. Every object with a temperature above absolute zero emits electromagnetic radiation, with the peak wavelength determined by its temperature. The extremely hot exhaust gases and the heated metal nozzle of a modern fighter jet emit intensely in the infrared spectrum. This is not a design flaw that can be easily fixed. It is a fundamental, inescapable law of physics. Engineers have tried to minimize this heat signature by mixing cool air with the hot exhaust and using specialized nozzle designs to disperse the plume. However, these measures only dilute the heat. They do not eliminate it. The sheer volume of hot gas required to keep a 30-ton aircraft in the air is immense. The resulting thermal plume can trail behind the aircraft for hundreds of meters, creating a massive invisible target. For years, military planners assumed that detecting these heat signatures from long distances was impractical due to atmospheric absorption and sensor limitations. But a quiet revolution in quantum physics has changed the game. Enter the Quantum Well Infrared Photodetector, or QWIP. This technology, developed and refined by researchers, including those in Iran, has turned the traditional stealth paradigm completely on its head. To understand how QWIP works, we must dive into the subatomic world. A quantum well is an extremely thin layer of semiconductor material, sandwiched between two wider bandgap semiconductor layers. Because this layer is so thin, only a few nanometers thick, it confines electrons in a one-dimensional space. This quantum confinement forces the electrons to occupy discrete, quantized energy levels, creating highly specific energy states. When an incoming infrared photon of light strikes one of these trapped electrons, it transfers its energy to the electron. If the photon's energy matches the gap between the quantum well's energy levels, the electron is excited out of the well and into the conduction band. This movement of electrons creates a measurable electrical current. By measuring this current, we can detect the presence of even a single, incredibly weak infrared photon. The true magic of QWIP lies in bandgap engineering. By adjusting the thickness of the quantum well layer and the composition of the semiconductor materials, scientists can precisely tune the sensor to detect specific wavelengths of light. This means a QWIP sensor can be customized to ignore atmospheric noise and focus exclusively on the exact thermal wavelengths emitted by a stealth fighter's Pratt & Whitney engine. Earth's atmosphere absorbs most infrared radiation, but there are specific transmission windows where the air is transparent. The most critical windows are the mid-wave infrared, from 3 to 5 micrometers, and the long-wave infrared from 8 to 12 micrometers. Conveniently, the thermal emissions from a jet engine's exhaust plume and heated fuselage fall perfectly within these atmospheric transmission windows, allowing long-range detection. Unlike traditional radar, which must emit a massive burst of radio energy to detect a target, QWIP-based infrared search and track systems are completely passive. They do not emit any signals of their own. They simply watch and listen. This is a critical tactical advantage. When a radar system scans the sky, a stealth pilot's radar warning receiver instantly alerts them to the threat. With passive QWIP sensors, the pilot has no idea they are being tracked. How did Iran, a nation under decades of strict international sanctions, manage to develop such advanced quantum sensor technology? The answer lies in a combination of high-level academic research and a highly coordinated domestic engineering program. Iran's top universities have quietly built robust physics departments, focusing heavily on solid-state physics, semiconductor fabrication, and quantum optics to bypass Western technology blockades. But academic theory is only half the battle. Practical engineering requires real-world models. Over the past 2 decades, Iran has managed to capture several highly advanced, intact United States military drones that crashed or were brought down within its borders or territorial waters. These captured assets provided Iranian engineers with a priceless treasure trove of cutting-edge optical and sensor technologies to dissect. Among these captured assets was the RQ-170 Sentinel, a highly classified stealth drone, and later, the MQ-9 Reaper. Iranian scientists systematically disassembled these aircraft, mapping their electronic architectures and analyzing their optical sensor suites. They paid special attention to the cooling systems and semiconductor materials used in the drone's infrared cameras, learning how the US solved the problems of noise and sensitivity. Replicating these sensors required advanced semiconductor fabrication capabilities, which are notoriously difficult to master. Standard silicon chips are not sensitive enough for high-performance infrared detection. Instead, QWIP sensors require exotic compound semiconductors like gallium arsenide and aluminum gallium arsenide. Fabricating these materials requires growing atomic-scale layers of crystals, one single sheet of atoms at a time. This process, known as molecular beam epitaxy, is the pinnacle of nanotech engineering. By heating ultra-pure elements in vacuum chambers, scientists can shoot beams of atoms at a substrate, creating ultra-precise quantum wells. Iran's ability to master this technique, despite sanctions restricting the import of MBE machines, is a testament to their domestic scientific focus. They built their own deposition systems and synthesized their own precursor material. But growing the crystals is only the first step. QWIP sensors have one major limitation. They must be cooled to extremely low temperatures to operate effectively. At room temperature, the thermal energy of the atoms inside the semiconductor is enough to knock electrons out of the quantum wells, creating a massive amount of background noise. To see the faint heat signature of a distant jet, the sensor must be cooled to liquid nitrogen temperatures. To achieve this in a portable, military-grade package, engineers use closed-cycle Stirling cryocoolers. These compact, highly reliable mechanical refrigerators use helium gas to cool the sensor to around 77 Kelvin in a matter of minutes. Reverse engineering these tiny, high-precision compressors from captured Western hardware allowed Iran to integrate QWIP sensors onto mobile ground stations and air defense systems. Once cooled, the QWIP sensor becomes an incredibly sensitive eye capable of seeing the universe in a completely different light. It can detect temperature differences of just a fraction of a degree from miles away. When mounted inside a stabilized multispectral optical turret, this sensor can scan the horizon, looking for the tiny localized thermal anomalies created by high-altitude military aircraft. On a ground-based tracking screen, the operator does not see a radar blip. Instead, they see a high-resolution thermal image. The cold sky appears as a dark, uniform background, while the F-35's engine exhaust plume appears as a brilliant, white-hot torch. The sensor is so sensitive that it can even detect the aerodynamic heating on the leading edges of the aircraft's wings, caused by friction with the air at high speeds. This aerodynamic heating is another physical reality that stealth cannot hide. As an aircraft pushes through the air, it compresses the air molecules in front of it, generating friction and heat. At Mach 1.5, the nose of an F-35 can heat up to over 80 degrees Celsius. This creates a distinct thermal silhouette that is completely independent of the engine exhaust, providing yet another target for sensitive QWIP sensors. Modern stealth tactics rely heavily on emission control, or EMCON. Pilots turn off their radars and communicate via low probability of intercept data links to avoid giving away their position. They fly in absolute radio silence, believing they are invisible. But this radio silence is completely useless against a passive QWIP sensor. The jet's physical presence and its heat emissions are constantly communicating its exact position to the ground. But just how far can these quantum sensors see? Critics of infrared tracking often point out that moisture, dust, and clouds can scatter infrared light, severely limiting their range compared to radar. While this is true in the lower atmosphere, stealth fighters typically operate at high altitudes above 30,000 feet, where the air is extremely thin, dry, and cold. In these pristine conditions, QWIP sensors can detect targets at immense distances. At high altitudes, the atmospheric absorption of infrared light drops to almost zero. Without water vapor to scatter the photons, the thermal radiation from a jet engine can travel hundreds of kilometers unimpeded. This allows a ground-based or airborne QWIP system to detect a stealth fighter long before it enters the range of its own air-to-ground weapons, thus striping away the element of surprise that stealth is designed to provide. To extract these faint signals from the natural background radiation of the sky, modern QWIP systems use advanced digital signal processing. By applying sophisticated noise reduction algorithms, the system can filter out cosmic radiation, solar reflections, and atmospheric noise. This software-driven amplification allows the sensor to lock onto a target that would be completely invisible to the naked eye or to standard thermal cameras. In Iran's integrated air defense network, these QWIP sensors do not operate in isolation. They are networked with mobile surface-to-air missile systems, such as the Bavar 373. By using passive infrared sensors to find and track the stealth target, the air defense system can calculate a firing solution without ever turning on its target acquisition radars, keeping the stealth aircraft's pilots completely in the dark until it is too late. When a missile is launched, it can be guided initially, using the passive tracking data from the ground-based QWIP sensor. The missile flies toward the target without emitting any radar signals that would trigger the jet's defensive countermeasures. Only in the terminal phase of the flight does the missile activate its own onboard seeker, which can also be a passive infrared sensor, leaving the pilot with almost zero time to react. Against a radar-guided missile, a pilot can use electronic jamming or deploy chaff to confuse the radar. But against a passive infrared seeker, these countermeasures are far less effective. While pilots can deploy burning magnesium flares to decoy heat-seeking missiles, modern multispectral QWIP seekers can easily distinguish between the rapid, intense burn of a flare and the steady, specific thermal signature of a jet engine. This vulnerability is causing a quiet panic among Western military planners. The entire doctrine of modern air power is built on the assumption that stealth provides near invulnerability. If relatively inexpensive quantum sensors can detect and track these $100 million aircraft from long distances, the massive financial investment in stealth technology begins to look like a historic, strategic miscalculation. This is a classic example of asymmetric warfare. A nation with a fraction of the United States military budget can use basic scientific principles and advanced material science to neutralize the most expensive weapon systems ever created. By focusing on the inescapable physical laws of thermodynamics rather than trying to match the US in radar technology, Iran has found a highly cost-effective way to level the playing field. At the heart of this asymmetric shift is the science of quantum materials. Unlike traditional materials, whose properties are determined by their bulk chemical composition, quantum materials derive their unique characteristics from quantum mechanical effects. By manipulating the physical structure of semiconductors at the nanometer scale, scientists can force these materials to interact with light in ways that do not occur in nature. In a practical QWIP sensor, millions of these tiny quantum wells are arranged in a grid, forming a focal plane array. This array is similar to the sensor chip in a digital camera, but instead of detecting visible light, each individual pixel is tuned to detect specific wavelengths of infrared radiation. This allows the system to build a highly detailed thermal image of the sky, capturing both the jet and its complex thermal plume. Iran's success in this field highlights the global democratization of high scientific knowledge. Through scientific journals, international conferences, and open-source academic research, the secrets of quantum well fabrication have spread far beyond the borders of the Western nations that pioneered them. Today, any nation with a dedicated group of physicists and a cleanroom facility can enter the field of quantum optoelectronics. For the F-35, this represents a profound threat. The aircraft was designed to operate in an environment where it could use its stealth to get close to the enemy, launch its weapons, and escape undetected. If it can be tracked from 50 miles away by passive ground sensors, its tactical utility is severely degraded. It is forced to operate further back, reducing its effectiveness and exposing it to interception by conventional fighters. Let's look closer at the physics of the thermal plume itself. When fuel burns inside the F-35's engine, it produces carbon dioxide and water vapor at temperatures exceeding 1500 degrees Celsius. As this gas is expelled, it rapidly expands and cools, but it remains significantly hotter than the surrounding air for a long time. This creates a massive, turbulent wake of heated gas that cannot be hidden by any radar-absorbent material. Some modern aircraft attempt to cool their exhaust by ducting bypass air around the engine core and mixing it with the hot exhaust before it leaves the nozzle. While this lowers the temperature of the gas, it also reduces the engine's thrust and efficiency. For a high-performance fighter like the F-35, there is a strict physical limit to how much cooling can be done without sacrificing the speed and maneuverability needed to survive in combat. Why use QWIP instead of traditional mercury cadmium telluride or MCT infrared sensors? MCT sensors are highly sensitive, but they are incredibly difficult to manufacture uniformly, especially in large arrays. They are also highly fragile and prone to defects. QWIP, on the other hand, denotes a mature gallium arsenide technology, which is much easier to produce with high uniformity and reliability, allowing for larger, more detailed sensor arrays. This uniformity is critical for long-range tracking. In a focal plane array, if some pixels are more sensitive than others, it creates a grainy image with high spatial noise, making it difficult to spot a tiny, distant target. The extreme uniformity of gallium arsenide-based QWIP sensors ensures that every single pixel performs identically, allowing the system to detect the faintest thermal signals against the uniform cold background of the sky. Iran is not the only nation recognizing the power of quantum sensors. China, Russia, and several European nations are also investing heavily in QWIP and related quantum technologies. The realization that traditional radar-based stealth is reaching its physical limits has triggered a global race to develop the most sensitive, long-range optical tracking systems, turning the sky into an arena of invisible light and silent hunters. The F-35 itself is packed with incredibly complex electronic systems, all of which generate heat. From its powerful, active, electronically scanned array radar to its central computer processors, the aircraft requires a massive liquid cooling system to keep its electronics from overheating. This heat must be transferred somewhere, and it is ultimately dumped into the fuel tanks or radiated out through heat exchangers, adding to the thermal signature. Using fuel as a heat sink is a clever engineering trick, but it has a major limitation. As the aircraft flies and consumes fuel, there is less liquid available to absorb the heat. On long missions, the fuel temperature rises, reducing its cooling capacity. Eventually, the aircraft must dump this heat directly into the air through heat exchangers on the fuselage, creating localized hotspots that are easily detected by QWIP sensors. Furthermore, while the F-35's geometric shape is designed to reflect radar waves away from the source, it does not prevent the reflection of thermal radiation from the sun. During the day, the metal skin of the aircraft absorbs solar radiation, heating up significantly compared to the surrounding air. Additionally, the flat upper surfaces of the jet can reflect the brilliant infrared glare of the sun directly into the sensors of tracking systems. All of these factors point to a sobering conclusion. The era of absolute stealth dominance is drawing to a close. The assumption that a military can achieve air superiority simply by shaping its aircraft to avoid radar is no longer valid. The physical reality of heat, combined with the rapid advance of quantum sensor technology, has created an environment where complete invisibility in the skies is physically impossible. How is the United States responding to this threat? The military is forced to adapt, investing in new technologies to counter passive infrared tracking. This includes researching low-emission fuels, developing advanced thermal barrier coatings, and experimenting with active cooling systems that use liquid nitrogen to cool the exterior skin of the aircraft in critical areas. However, these solutions add immense weight, complexity, and cost. Every pound of cooling equipment or thermal coating added to an aircraft is a pound of fuel or weapon to seed must be left behind. This is the tragic trade-off of modern aerospace engineering. To counter a relatively simple, passive ground sensor, the stealth aircraft must become heavier, less maneuverable, and even more expensive, further shifting the economic and tactical balance in favor of the defensive sensors. Let's return to the lab to appreciate the sheer precision of QWIP manufacturing. The layers of gallium arsenide and aluminum gallium arsenide must be grown with atomic precision. A single atomic layer too thick or too thin will shift the quantum energy levels, making the sensor blind to the target wavelength. This requires real-time monitoring during the growth process using reflection high-energy electron diffraction. This technique, known as READ, allows scientists to monitor the crystal growth in real time, counting the atomic layers as they land on the substrate. By watching the intensity of the diffracted electron beam oscillate, engineers know exactly when a single layer of atoms is complete. This level of nanometer scale control, once a closely guarded secret of a few elite Western labs, is now standard practice in advanced facilities worldwide. The captured US drones did more than just reveal sensor designs. They also exposed the software algorithms used to process the thermal images. By analyzing the onboard processors of a downed RQ-170, Iranian engineers learned how Western systems filter out atmospheric noise and track moving targets. This allowed them to design counter algorithms, optimizing their own QWIP systems to bypass Western electronic countermeasures. Modern Iranian QWIP systems are believed to use multispectral tracking. By detecting infrared light in multiple distinct wavebands simultaneously, the system can compare the ratio of intensities at different wavelengths. This allows the tracking computer to calculate the precise temperature of the target, easily distinguishing a real aircraft from natural background clutter, solar glare, or burning defensive flares. As we look to the future, the implications of this technology are profound. The multi-billion-dollar stealth programs that have dominated military planning for the past 30 years are facing a crisis of relevance. The simple, unyielding laws of thermodynamics, combined with the precise manipulation of quantum materials, have shown that in the silent battle between heat and light, the sensor will eventually win. This is the ultimate triumph of basic physics over brute force engineering. No matter how much money is spent, no matter how complex the radar-absorbent coatings become, they cannot rewrite the laws of thermodynamics. A hot object in a cold sky will always radiate energy. And as long as that energy is radiated, quantum physics will find a way to detect it, turning the stealth giants of today into the visible targets of tomorrow. The future of air warfare will not be defined by who has the stealthiest aircraft, but by who has the most advanced sensors and the smartest algorithms. The sky is no longer a hiding place. It is a transparent medium where every move is tracked by silent, passive eyes. This shift will force military planners to rethink everything, focusing on long-range standoff weapons and unmanned swarm systems rather than manned stealth fighters. This technological shift is also rebalancing global geopolitics. Smaller, less wealthy nations can now defend their airspace against the most advanced air forces in the world. By investing in quantum sensor research and domestic semiconductor fabrication, they can build a highly effective defensive shield that neutralizes the offensive advantage of stealth, creating a more balanced and contested global strategic environment. The F-35 will likely remain a highly capable aircraft, but its role will have to change. It can no longer operate under the assumption of complete invisibility. It must fly with support from electronic warfare aircraft, rely on heavy jamming, and operate at the edge of the contested zone, rather than deep inside it. The era of the lone, invisible stealth predator slipping silently through the night is over. Meanwhile, the quantum race continues to accelerate. Researchers are already working on the next generation of sensors, including Type 2 superlattice detectors and quantum dot infrared photodetectors, which promise even higher sensitivity and higher operating temperatures. The battle between stealth and detection has moved from the aerospace factory to the physics laboratory, where the weapons of tomorrow are grown atom by atom. There is a profound scientific lesson here. It reminds us that no technology is absolute. Every engineering solution carries the seeds of its own neutralization, hidden within the very laws of nature that make it possible. The same physics that allow a jet to fly the combustion of fuel and the generation of thrust are the exact same physics that reveal its position to the silent quantum eyes watching from below. As we look up at the night sky, we must realize that it is far more crowded and transparent than it appears. Above us, an invisible battle of light, heat, and quantum mechanics is constantly raging. The stealth giants of the past are being quietly watched by the quantum sentinels of the future, proving once again that in the world of science, knowledge and precision will always triumph over brute force engineering. Thank you for joining us on Science Aura. The story of stealth and quantum sensors is a powerful reminder of how basic scientific principles shape the modern world. If you enjoyed this deep dive into the physics of modern warfare, don't forget to like, subscribe, and share your thoughts in the comments below. What do you think is the future of stealth in the quantum era? I'm Dr. Sachi Vale, and I'll see you in the next episode.